Section 2.4, infinite limits. We're going to start off with the definition. Suppose that f is defined for all x near a. If f of x grows arbitrarily large for all x sufficiently close to a, we write this. And the way we would read that is, as in quotes down below, the limit of f of x as x approaches a is infinity. And then a similar case, suppose that f is negative instead of positive, but still grows arbitrarily large in magnitude or in size for all x sufficiently close to a, then we would write it a little different. We'd write the limit as x approaches a of f of x equals negative infinity. And I just kind of said it as I wrote it down, and you can see below the way we read that out. So the limit of f of x as x approaches a is negative infinity. In both cases, since the limit to exist, the function has to be approaching a specific number, and infinity and negative infinity are not numbers, they're more of an idea. So in both cases, even though we have a way to write the answer that it's infinity or negative infinity, it's still the case that the limit does not exist. So really what's happening here, we're taking a limit that doesn't exist and coming up with a way to write it, so we have a way to express the specific way in which the limit does not exist. So now let's write that for this picture that they've shown us. In this case, let's suppose that this kind of pinkish purplish graph here was y equals g of x. It appears that in this case we're looking at x is approaching 2 from the two sides, and whether we're coming from the left or the right, it seems like the function is heading up towards infinity. So in this case, I could say that the limit as x approaches 2 of g of x is equal to infinity, because whether we're coming from the left or right-hand side, as we approach 2, the function grows arbitrarily large and is therefore considered to be going to infinity. All right, let's go ahead and apply that idea to an example. So find the limit of f of x equals 1 over x minus 2 as x approaches 2 from the left and from the right. So for this one, since they've given us this grid, I'm going to draw the graph, and then we'll use the graph to answer the question. But I also want to show you in the next page how we could do it even if we didn't have a graph. So let's see. Just trying to find the middle line here. So there's our vertical axis. Here's our horizontal axis. I'm going to go ahead and just do a standard numbering on this. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And then the same in the negative directions. And then I'm just going to go ahead and rely on the graphing calculator for the graph. We'll get into more details about how to draw these graphs later, and you should have seen it before in algebra, but for now we're just going to kind of steal the graph from the graphing calculator, though I will show you that process over there as well. So I want to hit the y equals key to enter in my function. I have already typed it, y1 equals 1 divided by x minus 2. Do notice that I put parentheses around the x minus 2 to make sure that the calculator sees all of that is in the denominator. If you leave off the parentheses, you will get a different and incorrect graph. And then if I just hit the graph button, I'll see a picture. But the scale here isn't the same as what I have on my grid on paper. So if I go back to the home screen, above where it says graph in orange, it says window. So if I hit the orange second key and then that key, I get to select my window. And we numbered from -7 to 7 on the x-axis, and we numbered from -7 to 7 on the y-axis. So, and we used a scale of 1. So if I set that, then the graph here will match up with the grid that we've drawn. So now I'll hit graph again, and there's our picture. And what we can see is it looks like there's a vertical asymptote at x equals 2, and also the the x-axis appears to be a horizontal asymptote, and to the upper right, the function's positive, to the lower left, it's negative. So let's go ahead and kind of duplicate those ideas back on our notes. So at x equals 2, we had a vertical asymptote. So I will draw a dotted line there. We also had one on the x-axis, and the graph did something like this in the upper right, and something kind of like that in the lower left. So now what happens with the limits? They want the limit, if we look there, they want the limit from the left, and they also want the limit from the right. So we'll do both of those cases. So first we'll look at the limit as x approaches 2 from the left of this function f of x. And we'll just look at that on the graph. So if we're approaching 2 coming from the left-hand side, heading towards -2, it seems like the graph is taking off downward towards -infinity. So we'd say the limit as x approaches 2 from the left of f of x is -infinity. If we want to do that from the right, I'll go ahead and switch the color up there. As we approach 2 from the right, so coming from the right-hand side and approaching 2 and staying on the graph, it looks like the graph is taking off upward towards infinity. So for that one, we would say the limit as x approaches 2 from the right-hand side of f of x appears to be positive infinity. So because of that vertical asymptote, the graph is being kind of redirected either way up or way down, depending on whether we're coming from the left or the right. So we're using the graph to help us figure out whether, it's a negative infinity or the positive infinity. They only ask this, by the way, for the left or the right, but if the left and right are not the same, then as we learned before, we could say the limit as x approaches 2 over all of this function does not exist. Now remember, I said earlier that if the limit is negative infinity or positive infinity, that actually means the limit does not exist as well, but we have a way to express it if the limit is infinity or negative infinity. If we're getting different answers for those infinities, then we still have to end up saying that the overall limit doesn't exist. All right, let's go ahead and look at another example. Find the limit of f of x equals x minus 1 over x minus 5 as x approaches 5 from the left and from the right. So we're going to want to look at what is the limit as x approaches 5 from the left of f of x, and what is the limit as x approaches 5 from the right of f of x. We could do this by entering it into the graphing calculator, but I want to show you a way that you can spot that your answers are infinity and then how to figure out which type of infinity you're getting without the graph. So first of all, how do you spot that the answer is going to be either infinity or negative infinity from the left or the right? You can kind of see that by direct substitution. So suppose I take that 5 and I just plug it into the function. So I would get 5 minus 1 over 5 minus 5. In the numerator, I get 4. In the denominator, I get 0, and that's undefined. When you attempt direct substitution and the top is a constant that's not 0, and the bottom is 0, that always tells you that the function has a vertical asymptote there. You've got to be a little careful with always. Depends on some factors, but basically for most functions, if this happens, you're going to have a vertical asymptote. And that means your answers are going to be either infinity or negative infinity. So then how do you figure out which one it's going to be? Well, you can just do some plugging in. So let's take our function. Let's take some different x's and plug them in and see what we get out for the y value, or the f. Let's do it as a f of x value. Same idea, just different notation. So if we want to approach from the left-hand side, then let's plug a number in right here that is on the left of 5. So in this case, I could plug in 4.9 into the function and see what I get. And because I know the answer is going to be infinity, I really don't even care what I get as far as the number goes. I just want to look at what would happen if I did 4.9 minus 1 over 4.9 minus 5. And I know that the function, because of this 4 over 0 that I got right here, and it turning out undefined with a constant on top and a non-zero constant on the bottom, I know the answer for the limit is either infinity or negative infinity. So all I really need to pay attention to over on this calculation is the signs of the pieces, the top and the bottom. The top is 4.9 minus 1, which is positive. The denominator is 4.9 minus 5, which is negative 0.1, but more importantly, it's negative. And if you have a positive on top and a negative on the bottom, then overall you're going to get a negative. So if we plug in something on the left, and we can see that we're getting a negative, but we know the answer is supposed to be either infinity or negative infinity, then we can confidently come back over here and say the answer is negative infinity. If you want to test the right-hand side, then if you're approaching 5 from the right, then take some number that's bigger than 5, therefore on the right of 5, like 5.1, plug it in so that you get 5.1 minus 1 on top and 5.1 minus 5 in the denominator. Top is positive, bottom is positive, so overall it's positive. But because of this 4 over 0 piece, we know the answer is either infinity or negative infinity, and now we can see that we're getting positive numbers when we approach from the right, so therefore we know that the answer is positive infinity. And again, they didn't ask us, but if the answer as we approach from the left and the right is different, that does mean that the limit as x approaches 5 overall of this function does not exist. So there's a way that you can use some plugging in of numbers and just testing the sign to see if you're getting negative infinity or positive infinity for your answer. But make sure you've done the direct substitution piece first to see that you get non-zero in the numerator and 0 in the bottom. That's the thing that tells you for sure you're getting these infinities from the two sides. Let's look at another one. Trig function this time. So find the limit of f of x equals tan x as x approaches pi over 2 from the left and the right. So a couple things. One of them, our function tan x. If we want to think about what's going on there, we might want to remember that tan x is sine x over cosine x. That'll help us think about numerator and denominator. And then they want us to look at what's happening as we approach pi over 2. So the first thing I want to check is, do I suspect that I'm getting infinities from the left and from the right? And I can do a check on that by doing direct substitution. So what happens if I take f of pi over 2? Well, if I do that, I get sine of pi over 2 divided by cosine of pi over 2. And sine of pi over 2 is 1, cosine of pi over 2 is 0, so I'm getting that undefined non-zero constant up top, 0 in the bottom. So as I approach from the left or the right, I should be getting infinities. So we could, in fact, just go ahead and check this out by plugging in some number a little smaller than pi over 2 or a little bit bigger than pi over 2, but they've given us a spot to draw a graph, so I'm going to go ahead and approach it that way. So let's start off with a horizontal axis and add a vertical axis and put a scale that's nice for graphing a tangent function. So we have the 0 in the middle. Let's make every other one pi over 2. So this would be pi over 2. This would be 2 pi over 2, or just pi. And then 3 pi over 2. Sorry. 3 pi over 2. And then the same thing in the other direction. So a little bit of thought about sine and cosine on the unit circle. So on the unit circle, when are we getting these undefined spots for tangents? That would be when sine is 0. Sine is the y-coordinate, so we're going to get those undefined points and those asymptotes when cosine is 0. So cosine is the x-coordinate, which would be 0. Sorry about that. Cosine would be 0 here and here, okay? And when would sine be 0? Sine is the y-coordinate. So sine would be 0 here and here on the unit circle. So what does that mean? it means that when cosine is 0, which is at pi over 2, and 3 pi over 2, and negative pi over 2, in all those places you're getting a non-zero numerator over a 0 denominator when cosine is equal to 0, which are those green spots on the unit circle, which can be thought of as pi over 2, 3 pi over 2, or if you rotate the other direction, negative pi over 2. And then in between those, at these yellow circles on the unit circle, here and here, that's going to be when sine is 0, and that would be this spot. So there's a little bit for the graph. We have this idea that you have asymptotes at negative pi over 2, pi over 2, and 3 pi over 2. And you have intercepts at 0 and pi. Now let's just go ahead and cheat a little and look on the graphing calculator to see what's going on in between. So I'm going to enter the y equals piece. So that's just tangent of x. So y equals tan of x. And then for my window, let's try and do something kind of similar to what we had here. So let's see. It's not important that it matches exactly. I'll just do the part that I drew. So we'll go from negative pi over 2 to positive 3 pi over 2. So that's missing some of the blank spots on the edge of my picture, but this will still give us an idea of what's going on in between. And my scale was pi over 4, I think, because I did every other notch was pi over 2. Scale's not so important here. And the vertical scale really doesn't matter so much on this one for us to draw the picture. So let me just graph and leave the negative 7 to 7. So there's my picture. We've got our intercepts at 0 and pi over 2. And then it looks like in between the asymptotes, we're going from approaching the asymptote on the negative side on the left of each kind of section to going up and to the right on the positive side. So if I tried to mimic that here, we're down on the left side of a section, going through the intercept and then up. And then it would do the same thing over here. Down on the left, up on the right. So downward on the left side, upward on the right side. All right, so we got to squeeze in the answer to the question now. We did a whole lot of scratch work, but what is the limit as x approaches pi over 2 from the left-hand side of f of x? So we're approaching pi over 2 coming from the left towards pi over 2. We are going up towards infinity. So this would be positive infinity. What's the limit as x approaches pi over 2 from the right-hand side of f of x? So just doing a little bit different with the color here. So we're looking at pi over 2 from the right. So here's my pi over 2 line. We're approaching that from the right-hand side. So coming like this, it looks like we're going down towards negative infinity. So this one would be negative infinity. And we've run out of room, and they didn't ask us, but because it's positive infinity from the right and negative infinity from the left, that means that the overall limit as x approaches pi over 2 does not exist. All right, we're going to use this box here to summarize some of the things I said on the previous pages about vertical asymptotes. So the line x equals a is a vertical asymptote of the graph of f of x, or y equals f of x, if any of these conditions hold. So one of the things we talked about is direct substitution. So if plugging in for a, plugging in a in place of x, if that results in a constant over 0, where that constant up top is not 0. So if you do direct substitution where you plug whatever the a value is in for x and the top is not 0 and the bottom is 0, you're going to have a vertical asymptote at x equals whatever that value of a is. If you were looking at a graph and you could see that the limit as x approached a from either the left or the right, so I'll put plus or minus, if the limit from the left or the right was either positive infinity or negative infinity, in either of those cases, that also results in a vertical asymptote at x equals a. So if you look at the one below, they say find the vertical asymptotes of f of x equals x squared minus 1 divided by x squared plus x. What I would really think about there is that's going to happen anywhere that I could plug in, and the top wouldn't be 0, but the bottom would be 0. And if I'm interested in where the top and the bottom are equal to 0, then it would be good to factor this. The top is a difference of squares. We have x squared minus 1 squared, so that would be x minus 1 times x plus 1, using the idea that a squared minus b squared factors as a minus b times a plus b. In the denominator, we have a GCF of x, so I can factor that GCF out, and I get x out front and x plus 1 left. So first of all, where does the denominator equal 0? So if you look at where is this 0, if x equals 0 or x equals negative 1, then you're going to get a 0 denominator and therefore undefined fraction. And so you'd think also therefore a vertical asymptote. But if we look back up top right here, you also back up there, you need the numerator to not be 0 in order to get a vertical asymptote. And at negative 1, that makes this part of the numerator 0 also. In fact, if you think about reducing this, you could cancel off that. Let's do that in a different color. So you could cancel off that x plus 1. And if you did that, you'd just be left with x minus 1 over x. And we saw this before when we were looking at evaluating limits. If there's a factor that you can remove where the top and bottom are 0, that's a hole. So this function has a hole at x equals negative 1, not a vertical asymptote. Even though it made the denominator 0, it also made the numerator 0, and we can remove that undefined piece of the function in a way by canceling that factor off. So that's a hole, not an asymptote. But this zero denominator opportunity still remains even after we reduce. So when is that denominator 0? When x is 0. And if you put 0 in the top, you get 0 minus 1, which is not 0. So if you plug x equals 0 into this function, you get negative 1 on the top and 0 on the bottom if you look at the reduced, or the simplified version of it. So we're getting that non-zero up top and the 0 on the bottom. Now initially, if you plugged into the original right here, negative 1, you get 0 on top and bottom, and that's inconclusive when that happens. So you want to reduce and then see what happens after you reduce. So after we reduce, we're getting negative 1 up top, 0 on the bottom, which is that undefined type that produces a vertical asymptote. So then we could go ahead and declare that we have a vertical asymptote, or I'll just write VA at x equals 0. And they didn't ask us to do this, but maybe a quick look at the graph would be nice to kind of verify those things. So let's go ahead and head over to the graphing calculator and see what we can learn there. All right, so we'd want to start out by typing this function into the graphing calculator. So if I hit the y equals, I can enter it there. And I went ahead already and typed that in. And I typed the original function that they gave us, the x squared minus 1 divided by the x squared plus x. So I didn't type in the reduced version. And then I want to graph it, but if I do that originally, I'm still like in that window from the trig function. So if I hit second and window, let's go ahead and adjust this to what's kind of the standard window, negative 10 to 10 for the x values, 1 for the scale, and negative 10 to 10 for the y values with 1 of the scale. On the TI-84, there's a button that says zoom, and if you press that and choose zoom standard, it'll automatically do these settings of negative 10 to 10 for both the x and the y. So that's a nice shortcut on the TI-84. Anyway, let's go ahead and graph here and see if what we found out on paper is matching up. We said there was a vertical asymptote at x equals 0. And if I trace on the function here, it definitely seems like as we approach from the left, as we approach from the right-hand side, we are going down towards negative infinity. And if I approach from the left-hand side, I'm going up towards positive infinity. So we're definitely getting those kind of infinity answers and therefore a vertical asymptote. So that matches what we found on paper. And then we said there was a hole at x equals -1. So let's go ahead and see if we can kind of spy that by tracing. So as I approach -1 from the left or the right, I definitely, even though I had a zero denominator there in the original function, I'm not getting a infinity or negative infinity height as I approach that -1 value. Let's see if I can lock it in at -1. It's kind of hard to do. There we go. So if you look in the upper left, it says my x is -1 and my y value is NaN, which is not a number. So it's undefined there, and that's why we have the hole, but it's not a vertical asymptote because it wasn't a 0 over 0 sort of situation. If you're having a hard time locking in the value through trace, we can also just enter it in here. So I'm going to type calc and then type in the -1, which it already has there. So if it wasn't that number, you'd just type it in. So it's there already, so I can arrow that down. So here, let me show you that again. So let's say I'm not at -1, and I hit calc, then I can type -1 and go down, and it will put me at that specific number. On the TI-84, that works a little differently when you're in the trace mode and you're moving around on the function. You'll have a hard time hitting the -1, but while you're in trace mode, just type the number -1 and press enter, and it'll show you that x and the y value. But we're just trying to get a sense if what we did on paper is matching up with the graph, and it seems like it all is. All right, so that wraps up this section, and I will see you in section 2.5.